Okay. Wow, not as many people as was here on Wednesday. Must be Friday, huh?
Yep.
Damn it. Okay. So we've been going through Moore's circle. We started this example, right? It was a shaft with combined loading, so we had torsion and axial load. Okay. Fixed shaft. They asked us to populate a stress element based on the applied loads. Okay. So we found, picked an arbitrary point, right? And we're going to populate this stress element based on those applied loads. In order to do that, we looked at both our normal stress and our shear stress. Shear stress came from the torque. Normal stress came from the applied axial load, right? So we came up with our applied forces, or our applied stresses. We populated our element based on those applied stresses for a given state. Then we plotted those on Moore's circle. And they really wanted us to determine what are the principal stresses and the max shear that will be acting in this shaft, right? I mean, we're going to have the worst case demands in this shaft somewhere, okay? Based on this initial stress state that we can calculate based on the applied loads, okay? We input those into Moore's circle, and that allows us to see visually and to transform those initial stresses that we were able to calculate to our maximum stresses, right? Principal stresses being the ones where we don't have any shear stress. So that's our two stresses, or normal stresses on our x-axis. And then we have our maximum shear stress, which is the top and bottom of our Moore's circle. So, in order to figure out what those principal stresses and max shear stresses are, we need to figure out some more parameters about our Moore's circle that I drew so nicely. So we've got our center, right? That's always a good one to know. That's essentially our average stress over 2, which is 47.25 megapascals. Okay. Basically 95.5 is our normal stress, right, out here, plus our 0, we're on the y-axis, divided by 2. Our radius, okay, square root of this is where I get to go back and say that I was right. Remember this equation? What the fuck is it? This one here. Right? I wrote down another equation back here. And I had someone second guessing me. Where's he at?
He ran away.
Yeah. I sent him a nasty email. I don't think he's coming back. So there is another equation, and I think what I was getting confused about is it's not the average stress. Right? Square root of sum of the squares. So we can get the radius by either taking our normal stress on the x, right? Subtracting the center. So that gives us our horizontal leg. We're going to square that. And then we're going to add in our vertical leg of our triangle in order to get our radius, right? So if we had some arbitrary point, say it was up here, we're going to have a y leg and an x leg, right? This is our x leg and our y leg. So we can look at our x leg being whatever this point's sigma x is minus the center. Okay? The y leg being our shear stress at that point. Or we can go about it and look at it overall. We can say, all right, we're going to take the stress at x, or at this point, we're going to subtract out the stress at y at this point. We're going to divide by 2. That essentially gives us our x distance also. Okay? I wasn't reading that little negative. That was a negative. Maybe I wrote it as a positive and it was confusing me. Now I got these. Okay. mixed up. All right, does that make sense now? So if we use that equation down here, and we say sigma x minus sigma y over 2 squared plus tau xy squared, right? Square root. That's going to give us essentially the radius, which is 79.6 megapascals, okay? So we know our center is halfway between our two here, so 3 would be this guy sitting right here. That would be our center, or 47.25 comma 0, right? That would be the coordinate. That'd be the coordinate of our center, right? X coordinate being what we just calculated, which was the average stress, and then we have 0, right? It's on the x-axis. The center is always going to be on the x-axis, okay? Our radius we just calculated. That's this guy here, right? That's our radius. And we calculated that to be 79.6 megapascals. Well, we're looking, now that we have some of the components of our circle, right? The radius, the center, we can figure out any point along this circle, right? And we can also figure out the stresses at any given orientation from our known stress state, right? So these original 2 points are the stress state that we knew based on our shaft, right? The torsion and the axial load that's applied upon it. And so if we want to know, right, what's the maximum shear stress? Well, we know that that's the maximum values on our circle. Well, the maximum value on our circle is where our radius, right, is essentially the magnitude. Tau max, right? On both sides. One's going to be clockwise, one's going to be counterclockwise. We also have what we call sigma 1 and sigma 2, right? Those are our principal stresses. Those are the points on the circle where we don't have any shear stress or we don't have any y coordinate. Y is 0. So our max stress, or sigma 1, equals our center plus the radius, right? So we have 47.25 plus 79.6. We get 159.2 megapascals, right? That's our sigma 1. That would be this value right here, right? Our minimum stress, which is our sigma 2, right? Or our second principal stress, is going to be the center minus r, right? We're starting at the center. We're going to go all the way over to sigma 2. So we're going to take the center minus our radius. Well, we get 47.25 minus 79.6, or we get minus 32.36 megapascals, right? Compression. We also might want to know, well, if we look at this original stress state, right? We've got this little block H, right? This little point on the side of our shaft, and we know the initial stress state, but we really want to know what is the orientation, right? Where we're going to have our maximum stress, right? Our principal stresses. So what orientation do we need to move this H, right? Rotate it, essentially, to look at what plane in this shaft sees the worst case tension and compression, right? That would be this angle right here. Alpha, right? We have our original stress state, and in order to get to our principal stresses, we have to rotate clockwise by an amount alpha. Remembering that alpha, right? Alpha is 2 times theta, or 2 times the actual rotation in the real world. Well, we know alpha is essentially made up of a trigonomic function. We can call it tangent, or the inverse tangent, we know is inverse tangent of opposite over adjacent gives us our angle, right, alpha. Well, we know the opposite and adjacent. That's essentially what our coordinates of our first stress state point was, right? Sigma x and tau xy. So we can just plug these in. We'll say tangent negative, or inverse -1, 63.7. That's our opposite. That was our shear stress at the beginning we calculated, over our adjacent value. Well, that's going to be this x value, which is going to be the sigma x, right? Our initial stress state minus center. So 95.5 minus our center. 95.5 minus our center, which is 79.6. I sure did. Thank you. Okay, so 47.25. That should equal, shit, I wrote that way, so I hope this is right. It kind of looks right. 52.8 degrees equals alpha. So what does that mean? Well, that means theta equals 26.4 degrees. So if we rotated our stress block, sigma 2 was 32.4 megapascals. Sigma 1 was 159.2 megapascals. So if we looked at the stresses on these planes, right? So if we took our solid shaft that we have an imposed torque and axial load on, right? We initially found the stresses on a plane that were oriented perpendicular and parallel, right? Essentially looked at what stresses were going on around this little block. Well, the maximum stresses, or the principal stresses, are actually acting, say, on a plane that did something like this, right? So you're going to get these compressive loads and these tension loads in this shaft, and they're going to be oriented in this direction, right? Everywhere. So really this shaft is trying to get torn apart. And that's why, setting the axial load aside, that's why I can take a piece of chalk, or we talked about some failed shafts earlier on when we were talking about torsion. That's why when you twist a piece of chalk, its failure is a spiral as it runs around the shaft, because its principal stresses are actually oriented at, in that case, if you don't have any axial load, it's at a 45 degrees. And so you get this pure tension, and so the shaft wants to essentially pull itself apart at an angle, even though you're twisting it. Pretty cool though, right? Nice. Really sweet. Okay? And the axial load changes what that angle is, and we're able to calculate that based on Moore's circle and visually see it, right? So at 26.4 degrees, based on the fact that we're pulling on it now, we're going to get these tensile and compressive stresses. That's why in a drive shaft I showed you some of them buckling. Well, that's because in torsion you actually get tension and compression stresses in that pipe, right? Our drive shaft is essentially made out of a pipe, okay? And pipes are very, can buckle easily, right? So then in the compression sense, if the torsion gets significant enough, that means it's going to be having significant compression in it, and it'll actually buckle the drive shaft. Okay?
For your theta or your sigma 2 there,
Yep.
is that supposed to be negative because it's a compression, or can you state it as positive?
I've stated it as positive just because I denoted the direction based on the arrow. But yeah, it would be negative. You just wouldn't want someone to look at this and then imply that it's actually acting in the opposite direction.
Okay.
Okay. We're gonna look at another example where I gave you what the stress state is, okay? In this case, we have combined loading, which includes bending, which we are going to get to next, okay? But if you had a pipe, okay, that was fixed, maybe this is like a flagpole or something like that, okay? This flagpole, wind's blowing, the wind's blowing this flag out, so it's got a horizontal reaction, right, up at the top of this pole. It's got an axial load, basically the weight of the flag or any other elements they got hanging on it. And then for some reason, it's got a torque on it, right? You're gonna stick with me here. So it's got a torsion on it as well. So we've got a lateral load, an axial load, and this pipe, right, or pole is twisting. So we have all of these loading elements, right? Axial, bending, and torsion that are gonna create stresses in our flagpole, okay? So axially, we have this uniform axial stress, right, that was gonna act over the area, force over the area. So if this was 17 kilonewtons, we'd have a stress of a little over 8 megapascals based on the area. Bending, okay, which is essentially just a torque that's perpendicular to the axis of the member, okay, for a moment, creates both compression and tension, right, linearly distributed from what we will call the neutral axis, which we'll get to. So in that case, we could calculate what our maximum and minimum bending stresses are, right, which are going to be at the maximum and minimum, or maximum distances from our neutral axis, right, or the centroid of our section. So we got 49 megapascals there. And then if we had this applied torque that's along the axis of our member, right, with torsion, we know T equals, or the shear stress equals the torque times the max radius divided by the polar moment of inertia, right? So our maximum shear stress is acting at our maximum radius in our pipe, okay? We could calculate what that shear stress is. Based on this, we can use the powerful method of superposition, where essentially we're breaking down all of these stresses into their individual components, right? So we've got a stress due to axial load, we've got a stress due to bending, and we got a stress due to torsion, right? And all of those act at, say, this arbitrary point H on our pipe, okay? And so if we looked at a stress block at our point H, right, we've got these shear stresses. Well, we know from bending and axial load, we're not going to get shear stresses out of those initially, okay? We'll talk about that in a bit too, but for now, no shear stress comes from those two load sources. We do have torsional shear, right? And based on the direction of this torsional shear, right, it was acting off to the left on the top of our little square, so we're going to put our shear stress acting off to the left. Then our bending stress, right? Our maximum stress, if we looked at, say, on the other side of this pipe, we would actually have a tensile stress adding to a compressive stress due to the axial load, right? So we have a bending component and an axial component. On one side of this pipe, they're going to be additive, right? The compression from the axial load is going to be adding to the compression from actually bending the pipe itself. So we got these two, the bending stress and the axial stress are two stresses that we need to add together. So we have 49 and 8.35. So we end up with this final, right, stress state based on our applied loading. That looks something like this, right? We've got shear stress, which we know comes from the torsion, and we got this normal stress on the top and bottom face, or the Y faces, of 57.36 based on adding in our bending stress and our axial stress. Okay. So that just kind of sets up what we know. And again, if we went through the same process, once we had this stress state, right, known stress state, we could get asked a number of things, right? If we were looking for the worst case stresses in this pipe, right, or flagpole, we wanted to know what orientation those stresses are acting, we can use our known stress state, right, this stress block that we developed here. We can plot it on Moore's circle, and we're going to figure out what our principal stresses are, right? The max stress without shear stress. So again, we're gonna draw this. That's terrible. I need help. Boom. We know we've got, I know I've got compression, okay? So I drew my Moore's circle with the y-axis somewhere in the middle, knowing that I'm gonna have a data point on the left-hand side, right? Because normal stress on Moore's circle on the right-hand side of the y-axis is positive, so we have tension on one side and compression on the other. So we've got sigma n. We also have our shear stress, which is positive downward, which is counterclockwise. Shear stress clockwise is above the x-axis, right? This is all tau. So if we plot these, our known stress state, right? We have sigma x and sigma y and tau xy and tau yx, right? This is the axes that we're dealing with, if you look at that, right? So these essentially are the stresses that we came up with. Well, sigma x, we decided there is no stress, right, along the x face. And if sigma x is 0, then that means we're going to be back on the y-axis, right? So we're going to be over here. We also know that on that x face, our shear stress directions spin our stress element clockwise. So that means we're going to be above the x-axis, right? So we're on the y-axis, above the x-axis, the magnitude of which, or the coordinate, would be 0, 35.9, right? So we say up here, this is 0, 35.9, right? That's our sigma x coordinate, or x face coordinate, because we have a sigma and a tau. Similarly, we do the same for the y face. The y face in this case, we do have a normal stress. We know that it's compressive, so that's negative. We're going to be on the left-hand side of our y-axis, right? We're going to be in the negative values. And then we have tau yx now. That's 35.9. On that face, it's spinning us counterclockwise. So we're going to be below the x-axis. So our point is going to be essentially down here, trying to make this close. Something like that. So we've got our 2 points. This point, as I mentioned, is going to be negative 57.4, comma 35.9, right? Our sigma and our tau, or our normal stress and our shear stress. This is when I cheat and I do this. But I get to move this thing to cheat some more. Boom. That doesn't get old ever. Okay, so we got ourselves a Moore's circle. Our Moore's circle has a center like all Moore's circles do. Got this center. We know our center is the average stress, right? Which is sigma x plus sigma y over 2. In this case, we get negative 28.7 megapascals, right? Another one that's critical to know is our radius. In this case, I'm going to do sigma x minus sigma of the center squared plus tau xy squared, right? We're essentially just figuring out what is our y and our x components of our radius. Right? We've got this radius. We know the coordinates of one of our points, right? They're our x point. We're going to use that by figuring out what is the horizontal or x component of that point with respect to the center. Well, that would be our stress at 0 minus the center squared plus our shear stress at that point squared, square root, right? That Pythagorean theorem. And with that, I'm going to get 46 megapascals as my radius. Again, we know that these points are sigma 1 and sigma 2, right? Sigma 1 is going to be my center plus the radius, and sigma 2 is going to be the center minus the radius, right? So we have our sigma max, or sigma 1. Well, that's the center plus the radius. Well, in that case, we get 17.3 megapascals. Sigma min, or what we'd call our second principal stress, is the center minus the radius. Well, in that case, we get negative 74.7 megapascals. So those are our principal stresses, right? So we have a maximum tensile stress of 17.3 megapascals, a maximum compressive stress of 74.7 or almost 75 megapascals. So if we were analyzing this flagpole, we'd run through all of this analysis based on the cross section, right? We could figure out what the maximum stress is. We figured out our maximum shear stress based on the geometric properties of our pole, right? We've got max radius, we've got the polar moment of inertia. Bending stress, well, that's based on your moment of inertia and your cross section, okay, which we'll get to. Then our normal stress due to the axial load, well, that was over area. So you'd run through this whole analysis, you'd figure out that the maximum tensile stress and compressive stresses are what we've determined here. Well, maybe this pole is aluminum and it can't handle more than a compressive stress of 50 megapascals. Well, you start back at the beginning, right? Based on this loading, the demands will be as calculated based on the geometric properties of the pole. We would have to change either the loading or the geometric properties, right? We have to make it stronger, making the allowable stress higher. We'd have to make the pole diameter larger so we can increase our polar moment of inertia, right? We have all these moving pieces that would affect ultimately what we calculate as our maximum stresses. Right, again, our radius equals to 46 megapascals. Well, our radius is also tau max, right? Or what we would call our maximum in-plane shear stress. We're going to talk just a second about in-plane versus absolute. If we wanted to know what is the orientation of those stresses in the flagpole, right? We figured out what the stresses were both on the normal plane, right? If we were to cut the flagpole normal to our applied axial load, right? We know what those stresses are. We also know what stresses are on the plane perpendicular to that. But if we wanted to figure out what's the plane, right, or the orientation of our maximum stresses or our normal maximum principal stresses, we'd figure out what this angle is alpha, right? Which again is the inverse tangent, opposite over adjacent. Our case, the opposite over adjacent is 35.9, right? That was our shear stress of our X face. And then 28.2 megapascals gives us our adjacent. Is that opposite over adjacent?
The last one we did tau x y over sigma x minus center.
Yeah, we just need the coordinates. Yeah, that makes sense, because this is the, it's opposite over adjacent, right? This would be opposite, this would be adjacent. Well, this magnitude of our opposite is the shear stress magnitude, right? And the magnitude of our adjacent would be the coordinate of our center, which is our average stress, or, right, this is negative 28.7 comma 0, right? So then we put that in there. So that would be 51.4 degrees, or, as we know, in real life, it's half of that equals theta. So we would get that the, wow, that just feel like I shouldn't. All right, I'm not going to cheat. Not terrible. All right, if this was our block H, it would have to rotate our 25.7 degrees. Our maximum compressive stress, 74.4 megapascals. That is our sigma 2. And our maximum, tensile stress, sigma 1, is 17.3 megapascals. So if we went back and looked at our flagpole, right? If we looked at a plane that was at 25.7 degrees, that's where we would have our maximum normal stresses, right? Both in compression and tension. And in some cases, we could, say it was an existing flagpole and we added additional load and we had to maybe retrofit it, we could look at that and maybe you add in a spiral band of, say, reinforcement plates or something like that, right? To counteract the stresses at that angle. Maybe you wrap it in fiberglass or glass fiber reinforced polymer or something like that in order to strengthen it. All this making sense? We're going to keep going through a bunch more examples because this is a big part of this class, okay? Okay. Did I lose it? Yes. All right, so I added an extra page. All right, so we had an example. Your notes don't have this extra page, okay? So we are going to talk about what is the difference between the max in plane versus the absolute shear stress. Right? So previous examples we've gone through, they've asked about what is the max in-plane shear stress, okay? And some of the subsequent examples, and in the homework, right, I've issued a homework. It's due next Friday. And then there's also a quiz this week, which is not on this stuff, okay? But there's a quiz this week. It's open already, and it's open till the end of Sunday, right? So don't forget to do that. But we've talked about maximum in-plane shear stress, okay? Well, there's this idea of this absolute maximum shear stress. So if we look back at our in-plane first, Well, that's our maximum shear on our considered plane. Okay, so what does that mean? Well, we have our stress block. We're going to have stresses. Our coordinates are usually x face and y face. Right? Sigma y. Sigma y. We're going to have our shear stresses. And they're going to be our tau xy and our tau yx. We've gone through a couple examples now, right, where we've established what these shear stresses are in our x and y faces. Okay, we put them into Moore's circle, we create this circle, and on the top and bottom of that circle, right, that orientation gives us our maximum shear stress, right, the maximum magnitude of our shear stress in the given plane, right? In this case, we're always looking at the xy plane. Well, when we talk about absolute, or the book talks about absolute, or a homework problem talks about absolute, we want the maximum shear stress on all planes, right? So in this case, we've been really looking at xy, but really we're curious for absolute with respect to the x, y, and z, right? We jump into 3 dimensions. Okay, so I brought this fucking box because it took me a second to visualize this, okay? So say this was our stress block, all right? And we've been really looking at stresses on all 4 of these sides, right? Say this is the x-axis, this is the y-axis, just like I drew this damn thing, right? Okay? And we've been looking at if we were to orient or cut our flagpole at an angle, right? We were able to calculate based on Moore's circle, okay, what are these stresses going to be on these 4 sides? And we've been assuming, right, we're going to continue to assume that we're dealing with plane stress. So that means there's no stresses on this face or this face, right? This would be the z face or the z-axis, okay? And there's 0 stress on the front face or the back face of this little stress block, right? So we rotate this stress block and the stresses change, right? We get different shear stresses and normal stresses as we rotate this thing, okay? But now when we want to know what the absolute maximum shear stress is regarding all planes, well, now we've got to consider, even though we're assuming that our normal stresses are 0 and our tau, say zx, and our tau zy is 0, remember those? Okay, we had that original 3D block just like this. And we have, you know, in a 3D world, there'd be stresses here. Well, in plane stress, those stresses are 0, but all of those stresses in each one of these planes has its own circle on Moore's circle, okay? And we essentially are plotting 1 circle, but in reality there's 3, okay? How does that work? Well, I'll show you here. Just blowing minds. So we've got our stress block, right? And this is x, this is y. And acting out of plane, right? Out of our paper is this z-axis. So again, we've got all of these shear stresses. We've got our normal stresses. We've got tau xy, tau yx, sigma x, sigma y. But in reality, like I showed with the cardboard box, right, we have this assumed stress, sigma z, which is acting out of the page and into the page. Well, it's 0 for plane stress. Well, 0 still has a place on our coordinate for Moore's circle, right? If we go back up to here. 0 is right here. Okay? So if we were to plot the stresses on the z face, it's going to plot right here at this origin, right? 0, 0. So if we were to look at the fact that we originally started with our plane stress, right? It looks like this, but we know that it's 3D, so we've got this z stress acting, or z faces, right, front and back of this block, okay? Well, now we can draw a stress block. We've drawn a stress block, right, for this, where we have x and y coordinates, okay? Well, if we flip the block and now we look at a stress block that now has, say, the Y and Z faces, okay? And then we could flip it, see, this way, okay? And we would have, say, the X and Z faces, right? We could have essentially 3 more stress states, or 2 more stress states, looking at the other planes, right? X and Z and Y and Z. And so if we drew those out, we have Z and we have Y, right? We're going to have sigma Y. We also have, if we looked at X and Z, we're going to have sigma X, right? And that's all we're going to have. Those are the stress blocks if we're looking at those planes. X versus Z, Z versus Y, right? We only get sigma Y. We get no shear stress on this because we know because of plane stress, right? Because of plane stress, sigma Z equals tau ZX equals tau ZY equals 0, right? So if we ever look at those stress states, right? Essentially looking at a different side of this 6-sided box, right? If we looked at a different side, these other 2 sides here are the 3 sides, sorry, 4 sides. We would get, these are our stress blocks, right? 0 for shear stress, 0 for normal stress on our Z faces, and we would just get our sigma X and our sigma Y. So what does that look like with respect to Moore's circle? That just doesn't look right. So we do something like this, right? This was our Moore's circle. We know it is clockwise up here, counterclockwise down here. This is tau, positive downward, sigma normal, right? Those are our coordinate axes for our Moore's circle. And say we had an initial stress state, right? Just like we did for the flagpole. We've got X and Y coordinates on this block. We get stresses. We've got, say, a tau XY, which is a tau YX. And we have normal stresses just like we did. And we plotted those points. Maybe it was here. Maybe it was down here. Right? We're going to get a circle. Maybe it does something like that. And so we're going to get out of this, right? This was sigma X, This was sigma X, tau XY, right? That's our coordinate. This was sigma Y, tau YX, right? That was our coordinate. We can get our center, we can get our radius, essentially just doing what we just did in the previous example. Well, if we look in a 3-dimensional world and we're looking at the worst case absolute maximum shear stress, we got to look at all sides of this box and the fact that this box, right, it can rotate this way like we've seen it do, right, with this Moore's circle, but it can also rotate this way and it can also rotate this way. So it kind of can do all of this shit, right? Wish I had like a 3D visualization of this thing, right? It does all this crazy stuff, right? And as it's rotating, based on its initial stress state, I don't care if we had 0 stress front and back, but as we start doing this, we actually end up starting to get stresses on all faces of this block, right? At any given orientation. In order to see that, we need 2 more circles, right? We need the XY or the XZ plane and our XY plane. Well, we know one more coordinate. This is sigma Z tau ZX, right? Essentially, or tau XZ. It's always going to be at this origin. And we call that, right? This was, we go back, this is sigma 1, sigma 2. We call it sigma 3. Okay, and sigma 3 equals sigma Z equals 0. So our XZ plane is a circle that's based on our X point, right? Our sigma 1 and our sigma 3. And our YZ plane is a circle that's made from sigma 2 to sigma 3. So we end up getting 3 circles. If I can draw them. Let's see, what color should I go with? So we get these 3 circles on Moore's circle, right? Or on our graph here. We have one that's the relationship of our X or our YZ plane, and we have one that's the relationship between our XZ plane, and then we have the one where we have our plane stress, right? The one in the XY plane, the one that we've been playing with. Well, as you can see, if we in our plane stress state, right, the XY state, if we are not including the origin, right, we deviate outside the origin, then that circle that includes our Z face actually makes a bigger circle, right? If I show you, you have one of these in your notes. This one here, right? If our sigma 1 and sigma 2, right, that's our in-plane stresses, maximum principal stresses. If the origin lies within our initial circle, then we know that our absolute maximum shear stress is also the in-plane maximum shear stress, right? Whereas if we have this condition, where our X and Y plane, right, sigma 1 and sigma 2, are outside of the origin, whether they're both positive, right, if we have both normal stresses in tension, or both normal stresses in compression, well, that makes that our in-plane shear stress, which is right here, right, this is tau max in plane, is less than our tau max absolute. Right? Damn, it's already time. Just having so much fun. Okay. Well, we'll continue with an example on Monday.